would all be dead. Humans can't survive without it, but we don't only use water for biological purposes. There are so many other ways in which we use water, especially when it comes to providing power to help us as humans do work. Hello, my name is Elyce DPA and I'm from Spalding County. Today I will discuss developments in hydropower, specifically how it has worked in the past, how it is working now, and the plans for hydropower in the future. Hydroelectricity, in simplest terms, is electricity made by the means of using water. Hydropower is made by using a turbine turned by the flowing of water to provide a generator to generate electricity, to power a generator to generate electricity. Hydropower systems go back over 4,000 years, where they were used to create mechanical energy. An example of this kind of system is the water wheel, which was used to do things like irrigating, grinding grain, powering sawmills, and supplying power to people in the area. This kind of process dates back to about 2000 BCE, and although there are many differences between now and then when it comes to hydropower systems, there are also still many similarities. The modern hydropower turbine started around the 1700s in France. The beginning of this technology was when Bernard Forest de Belvoir wrote Architectural Hydraulic. The next major step in hydropower was in the 1880s when hydropower systems started using dynamos that were driven by water to provide arc lightning to produce light, using direct current technology. When the breakthrough of alternating current happened, it led to many things with hydropower, because now power could be transmitted over longer distances. This breakthrough led to the first U.S. commercial installation of an alternating current hydropower plant in 1893. The Redlands Power Plant in California, where the hydropower system was installed, used Pelton water wheels that were driven in the Mill Creek near the plant. A three-phase generator was used in the plant to guarantee consistent power would be provided. The advancements in hydropower throughout the last century have helped it become an integral part in the renewable energy mix in the United States. In 1902, the Bureau of Reclamation was established, and it is now the second largest provider of hydropower in the United States. The U.S. Army Corps of Engineers was authorized by Congress in the 1920s to build many hydroelectric plants, 75 of which are still being operated by the Corps. Those plants make the organization fifth in the ranking of electricity providers in the U.S. The next development was in 1929 when the first major pumped storage plant was introduced to increase hydropower capacity in the Housatonic River. In 1933, the Tennessee Valley Authority was given the task of controlling flooding and irrigation through the rivers in Tennessee. And today, they operate 29 hydroelectric dams and a pumped storage facility. 2 years later, in 1935, the authority of the Federal Power Commission was expanded to all hydroelectric projects built by publicly or privately owned utilities engaged in interstate commerce. When people think of hydroelectricity, most times their first thoughts will be things like the Hoover Dam, which was built in 1936 to provide irrigation water, control flooding, and provide power to the surrounding area. Many similar dam systems were built in subsequent years. President Franklin D. Roosevelt played a huge role in the development of hydropower technologies, including in 1937 when he signed the Bonneville Project Act. This act established the Bonneville Power Administration, which was over the Bonneville Lock and Dam. Another impact that President Roosevelt had on hydropower was the New Deal construction programs he implemented. These programs largely boosted hydropower usage, causing it to account for 40% of the electrical generation in the United States in 1940. This more than tripled the capacity of 20 years earlier, and the construction of one dam alone could employ around 10,500 workers. About 30 years later, in 1968 through around 1974, the United States became much more environmentally cautious, and subsequently launched many regulations and acts designed to protect natural resources. 1994 brought about the establishment of the Hydropower Research Foundation. This foundation was created to facilitate research and promote affordable and clean hydropower solutions. In 2005, the Energy Policy Act was signed, and the goal was to combat growing energy problems. The act provided incentives for multiple types of power, including hydroelectricity. In 2009, the DOE created the Water Power Program, which invested in upgrades to the nation's existing hydropower facilities to make hydropower even more cost-effective and productive. Smaller hydro projects were promoted in 2013 when President Obama passed the Hydropower Regulatory Efficiency Act and the Bureau of Reclamation Small Conduit Hydropower Development and Rural Jobs Act. The Hydropower Vision Report, released in 2016, describes the ambitions of hydropower now and in the future. In the current era, we have begun to expand generator designs to exploit more water energy sources. These newer types of generators include small-scale or micro-hydro, wave power, and tidal flow systems. Wave power and tidal flow systems are also grouped under the term marine hydrokinetics, or MHK. Whatever the design choice, these newer designs are generally intended to be more efficient and less environmentally impactful when compared to a large river and dam projects of the last century. In all cases, the choice of generator design used should be driven by the water source available, the required power, and the budget. Often in rural or underdeveloped regions, micro-hydro may be the answer to local power needs. There are many types of micro-hydropower designs. These designs all share a commonality of being smaller versions of what many people like to think of as hydropower, with lower cost and lower environmental impact. Broadly, these generators fall into two main design categories, the turbine or the wheel. Small turbines can be placed as a free-floating structure attached to a riverbed with cables, for example. They also may follow a design similar to the one shown in this illustration, where a riverbank has been modified with a culvert, incorporating a drain-style turbine. This particular design is capable of producing from 15 to 100 kilowatts, according to its manufacturer, enough for around 10 homes in the U.S. per generator, maybe more. This particular design is also safe for marine life, being no worse than a small rapid. Turbines may also be added to the outlet of existing small lakes or ponds, capturing the existing outflow for local energy. The other broad design style is the water wheel. Beyond the old school designs of a large exposed wheel with directed water flow, now we have designs such as this one illustrated here. This particular generator is designed to be placed in a stream or river with currents as slow as 2 miles per hour. Even at this slow speed, the leading ramp design, combined with the slotted design of the water wheel, is efficient enough to produce usable wattage and is also safe for the environment. More futuristic designs include marine hydrokinetic designs, which are some of the longer range of engineering challenges. While there are some installed plants producing power, the majority of these generators are still in the design and test phase. Wave power typically involves a floating arm system, usually attached to hydraulics, which takes the pulses of the waves and turns it into a relatively smooth form of energy. Since these systems are in the ocean, they have the potential to be exposed to very large storm surges, so they must be designed around challenges like these. Due to this, many of the designs include safety features that retract the arms when storms are sensed. This adds to the complexity of the project, and consequently the cost. But the cost is worthwhile due to the amount of energy able to be produced and the small footprint made. Another advantage for this system is that it opens up other locations to get hydroelectric power from, besides the classic location, rivers. An additional development in MHK systems is the tidal flow turbine. Some of these turbines are even hubless, like this one here. This particular design is safe for marine life, despite it being a large turbine, due to the lack of a small solid hub. Hydropower systems, as you can see, can be very useful and very adaptable to your specific circumstances. Today, I brought with me a hydropower system I have built myself. I have taken a simple permanent magnet type electric trolling motor and encased the edge of the propeller with a bucket I bought at Home Depot to increase the pressure on the blades, therefore increasing the efficiency of the system. Due to the type of motor being used, the transition of it from motor to generator is a simple one. The system is designed to attach to the outflow pipe of our farm pond. The spinning of the motor will provide electricity that I plan to use to power lights around the dock at our lake. This is an example of microhydro that could be replicated for many different cases. It is a low power system, but it is a way to recycle something that, like the motor, that would have been thrown away otherwise, and to be able to do something useful with it. Today, I have covered hydropower and its different systems throughout the past, present, and future. I have discussed the range of systems from the huge multi-million-dollar systems of the last century like hydroelectric dams, to the medium-sized systems like marine hydrokinetic designs, and even simple systems you can create at home. I hope to have given you insight as to what is going on in the realm of hydropower and maybe even inspired you to look into these systems yourself. To find the future of electricity, you may not have to look further than the water flowing all around you.